Thanks, guys, for having me. So, so I'm Colin, and normally this picture would probably, garner a few chuckles, but I imagine you guys have had more snow than we have this winter.
Was that from Cambridge?
Yeah, exactly. I'm a year-round cyclist, part crazy. I do a combination of many things in my day-to-day life, from coding to talking to doing finance stuff, and I've done actually a bunch of talks recently on responsive web. So this is a little bit of a departure from that to talk about mobile apps. Before we get going, I do want to do a shameless plug. So Velocity's coming up. Anybody in the room actually going to Velocity this year? Santa Clara? Oh, maybe you should go. You should go to Velocity because it's in Santa Clara, and you get to talk about geeky awesomeness. But this year you can learn about finance too. At the last session of the tutorial with yours truly, you get to get more awesomeness with geeky finance stuff. That's my talk, how to convince your CFO that performance matters, and I'm looking for people to pad the audience, being the last session before beers. Without any more ado, so I don't think it surprises anybody, mobile's kind of a big deal. In the next 45 minutes, nice quick stat, 11,000 babies born on this planet at the same time, some 80,000 smartphones born on cellular networks in 45 minutes. It's kind of a big deal. And it's also kind of garnered the debate, right? Mobile web versus native apps. And we've had the back and forth for many platforms, whether it be Facebook or Twitter or anybody out there debating the merits of one versus the other. Of course, debating native versus web doesn't end well for anybody. But I will submit that I think that there is something to be learned from mobile apps, from the browser world. We've seen when we saw native apps start to pop up, the world was pretty homogeneous. It was really IE. But since IE has, since smartphones have really come to their own, the browsers have also evolved quite substantially. And it's in this evolution that I think, and I want to submit to you, that this is where native apps have the most to learn. Because at the end of the day, all of the changes that have happened in browsers have been fundamentally about taking this graph at the top, we have CPU and bandwidth, we've got one depending on the other, CPU depending on bandwidth, and all the optimizations that browsers have done have been focused on getting kind of a bottom result, where you get this compression of saturating your bandwidth and getting the most out of your CPU to get a faster website. And these are the sets of optimizations that I want to kind of talk to you about that didn't exist prior, 7 years ago, really. So we've got a number of things, and just to kind of highlight, we've got things like the preloader, or the speculative parser, or the look-ahead parser. You've got prefetching with DNS, prefetching pages, prefetching resources. You've got connection pool management, and I'll talk about that a little bit. You've got HTTP2, dev tools, nav timing, enhanced security, and ciphers, and SNI. The browser's evolved quite substantially over the last 5 years by itself. But yet the native apps haven't. Now, what this is going to come to, and what's what I want to kind of tease out is from a set of research that I did. I took apart. You don't actually need to watch these videos. They're just me tapping through apps and with a camera and a stopwatch. And so I've went through and looked at a number of apps and looked at the characteristics of these native apps. How do they perform? So stopwatch, camera, and PCAP to track down what's going on across the wire. And so I want to share with you some of these results of what's been going on. And so the kind of 5 things that I'm going to kind of really talk through. Number 1 is about the preloader. connection pool management, dealing with stale caches, RUM, and SNI, H2 type stuff. And I've also got some extra stuff if we've got time or want to talk more through it. But. So let's talk about the preloader. See, it's like a scout. It's a drone, yeah. I wondered, like, when I was putting these together, I was like, I don't know if I'm tired or if any of these will make sense. Everybody familiar with the preloader, the speculative parser? A few nods?
Yeah.
All right. So for those that may not have nodded, the bottom line is most of the modern browsers all have at least one thread, if not whole microthreading architecture. It's going to go ahead and look at tokenized HTML ahead of the DOM being processed to go and find other CSS, JavaScript, any other dependent resources and try to load in them early and get them pushed into the network buffer. So that way, by the time that the DOM gets evaluated, you've got now all the resources ready to go. And this is probably one of the biggest boons for modern web browsers. So at the end of the day, you get a waterfall that looks like this, where you see one resource depending on the next resource, depending on the next resource. And you get something a little more squished up, because you get all the other resources, particularly JavaScript and CSS, all pushed up in the network, pushed it up early, and you get a faster loading web page. Okay. So that's cool. Let's take a look at what happens underneath the hood. Let's take a look at CNN. And you'll notice that, well, CNN has the same kind of problem. This is not unique. And all these examples are not unique to any specific app. But you see a sequence of events that happens from a JSON call being made, an AJAX call, or not AJAX, but like an API call being made. That call is evaluated, it spills some stuff on screen, it uses either asynchronous or asynchronous image loaders, and starts spilling those images on, and it all depended on a sequence of events. Those images are not being loaded while it's processing and building the UI. It's built at the time of display. In fact, and I won't show it to you here, but a lot of the images that are shown, this is CNN the news, so the images for each of the news articles are all loaded. They're using some asynchronous. As you scroll, more content is loaded, but it's loaded in some cases a little too late. But at the same time, you're wasting time because it could have downloaded some of these just below the threshold. As the user would have gone through. So this is, a common case where you see where the browser would have helped and would have stuffed for these images. And in fact, I'll just make a sub-point here about API calls. Often there tends to be collections of API calls, and where one depends on the next. Let's get the profile. From that profile, I'm going to determine their shipping address, or a sequence of different API calls. Again, API calls are often sequential, and so those kinds of things with a preloader could have been kind of batched together rather than being sequential. So this is the kind of the intro here, but number one, if you're going to use building anything, definitely look at how do you make your images asynchronous. There's a couple of good asynchronous loaders there, but you're ultimately going to build your own preloader, right? So anything that has insight into your application, there's no standard way because it's not like a browser where a browser has HTML and CSS and JavaScript. So anything you're going to build, you're going to have to build it so that you know how to analyze and look at your JSON payloads and figure out what images or what resources are going to be needed. And so what I'm really trying to suss out is the difference between loading up UI elements and letting the UI drive when to load them versus loading up the network and waiting for the user to catch up with what the network has already requested. So the Ion is a good asynchronous image loader for Android and worth looking at. Yeah.
What about also bunching up as much JSON as possible to one call instead of a zillion like the
Yeah, and actually I'm going to mention this a little bit in the connection pool, but absolutely, right? So one call versus many calls, less is always better, right? Especially if you can send more payload, especially on cellular connections where you've got a lot of that round trip time back and forth, back and forth, back and forth. Yeah.
Yeah, actually, I also know another library that works pretty fine.
Yeah.
Picasso is doing a good way of asynching, and also Volley from Google doing the same thing. So, and also I have tried Ion, but the most easiest one to deal with, and also for performance stuff, I think Picasso is doing a good job.
Yeah, yeah. So we want to balance the combination, because the first sets of the image loaders most people will do is they'll make it synchronous. They'll create the widget, they'll create the HTTP URL connection, wait for the payload to come, read the bytes, load the image, move to the next one, rather than just firing off network connections and letting them draw in asynchronously when they come back. Cool. So that's preloaders, but let's talk about something a little more interesting. So let's talk about connection pools. And this is probably the biggest difference that I've observed when it comes from mobile apps to browser activity. And really, the browser has done a lot of work to optimize its own connection pool. But let me use an example. I'm going to use the Velocity app. And this is, again, not unique to the Velocity app. I've seen this on a lot of different apps. And when I start profiling it, you'll start to see a typical waterfall like this, where you see images and various content being loaded as the app spins up. Looking at a connection view, you see the right kinds of things happening. You got some connection pool, some connections being reused. As one connection is currently busy, the OS spins up a second connection and it reuses those, and on they go. You do notice, actually, I'll just point out, you see those X's on the urban airship? Those are X's where the connection was terminated. And we're going to see more of that in a second. So again, connection view, when I start looking into the application, and a little gap there, that's just me poking around. But you see on the right, let me zoom that in for you. This right here is looking at the schedule, but you see all these connections. And what's happening is each one of these icons here is firing up a connection to go get this icon, and then it's promptly closing the connection, closing the connection, closing the connection. So you're spinning up a new connection to go get it. On mobile apps, unlike a browser, you have full control of the connection pool. You have the control to close your connections. Whereas in a browser, you have it's out of your control. The browser decides when to close a connection and when to load it up. Which has a number of nuances. And maybe I can kind of dig into some of these nuances one by one. At the bottom of the problem is you've got a number of different thresholds of how many connections in the connection pool you can have. So with Android, if you have to deal with very old devices like Android 2.2, I'm very sorry that you only have 4 connections and these are OS-wide. So you've got a max number of total connections and max connections per hosting. Modern Android, you've got 35 connections and 6 per host. And in iOS, it's fairly similar. You've got 4 connections per host, max connections of 15 with iOS 7 or later. You can override the number of connections on Android if you're able to set the global preferences, so you can move that up from 6 to a higher number. But generally speaking, your apps are going to be limited by the number of connections. Yeah.
Do you know why they would have went down? I mean, they went from.
Well, yeah, I don't know. Yeah. I suspect it's probably trying to balance performance and congestion on the connections. So if you think about it, most browsers are sitting in the same kind of connection pool size per host, 4 to 6.
Right.
So I suspect it's really just trying to follow a best practice and force, rather than trying to get a faster API, make sure we're not losing packets because we're opening up more connections, I suspect is the bottom line. But the Android, the early versions of Android are kind of painful, especially when you start looking at the ecosystem. Now, I'm sure you've seen versions of this in different various flavors, but the red there, that's the Android 2.2, well, 2.3, up to 2.3. So that 20% is a pretty painful group of users. Now your demographic might be slightly different, but when you remember you possibly are dealing with 4 system-wide or even 10 system-wide. And these are system-wide, so you've still got your background processes for your mail and Facebook and all those other systems that are chewing up a couple connections by themselves. So you're competing against the OS. Yeah.
In that case, I don't know how many people are writing apps right now for that, but the potential is there that your app just wants one, but you're running on a phone where the person's got loads of stuff going on, and your app looks like it doesn't work, right? Because you can't get a connection? Is that...
Yeah, possibly. Now, often, because the OS is in control of the connection pool, you're going to see the OS start to starve off connections that look a little idle. Mm-hmm. Which is actually interesting by itself, because you do have that your application could be starved off if there's another thread that's running that needs to have a connection, right? So there's this constant competition, and because unlike a browser, the browser knows what its primary is. Apex request came up, and so it knows where the HTML is delivered, and that's got higher precedence over other sub-resources, the other, maybe beacons or image shards or things like that. Those are low priority connections. So the browser manages those priorities of connection pools, connections in the pool. The OS, your Android OS or iOS, doesn't have that same knowledge of which host names are going to be reused again, and which ones are just used and then forgotten about, one-time use case. So there's a little bit of ambiguity in here of these pools. So where does this plays out in a couple ways? I was saying that. So number one is around that Apex request. Now, if you've got a number of pieces of infrastructure that depend on like cookies for load balancing, cookies for session tracking. Because there isn't an Apex request, you're typically going to see these, possibly parallel connections happening, right? So if you spin up a bunch of API calls in parallel, they can be executing at the same time, and because there's no single Apex request, like in a browser, you're going to set all of that load balancing, all the session cookies, all in parallel. You're going to set it twice or 3 times, depending on what's happening on the wire. So there's an Apex request issue that you have in browsers, but you don't get in mobile. And so you need to be aware of the cookies that are there, and other infrastructure that might be depending on it. But there's a bigger issue here around those connections. So closing connections and opening them up has a larger impact, especially on a cellular connection, right? So as you close off connections, you're going to run into the antenna starting to spin down. And as it spins down, it will move into different modes as it starts to talk with the resource scheduler. As the antenna, because remember, cellular is a shared environment, you need to get allocations of time on the tower to send or receive. And as you close off connections, you're telling the antenna you can power down, you don't need to request. You don't need to be keeping active with the tower. And then a few moments later, you're spinning up, saying, I need a new connection. You're now forcing the antenna now spin back up, and now need to move from either a long DRX or to a short DRX to start to say, hey, I need to get some time slices to start making my next request. I need to open up a connection. I need to send my handshake because I don't have a connection already open. So an LTE, that could take from anywhere 10 milliseconds to 100 milliseconds just to spin up the antenna before you can start firing away. If you're in a higher lossy connection environment, that could be quite, that could actually magnify itself quite a bit. There's been some stats out there that in high congestion times you can see like 30 requests before you get one packet of data out, just to try and gain your schedule on the antenna. Oh, that's what's supposed to be here. Yeah, I'll skip through that. So, what can you do about connection pools? So, we have a challenge if you're starting to close your connections, or if you're competing with resources. You fundamentally have control of the connection pool. And you should be taking advantage of it in the right places, but also not trying to be too smart, too clever about it. So first off, don't close the connections implicitly or explicitly. Let the underlying OS close them as they time out or as other connections are required. Because that will, at least if you've got your application lifecycle, it's going to keep the antenna awake. If you close them down, you're giving the antenna permission to start spinning down. Aggregating beacons and API calls. So in a lot of cases, you might have beacons, and I've seen this actually quite frequently, where you'll have beacons that will fire typically every 30 seconds, right? Which has its own set of challenges, because with the connection pools, most connection pools will time out around the 14 seconds. So 14 seconds of idle, the OS will start closing down those connections. And then you've got the antenna starting to spin down. If you're beaconing every 30 seconds to say that the user's interactive with your app, the user's still here, hasn't made any data calls, but you're beaconing up, then you're causing the antenna to spin back up, draining the battery, and you're also taking time to send that payload out and blocking other requests. Yeah?
Wouldn't it be just as expensive to keep the antenna going during the entire time?
Right, yeah. So that's why I'm suggesting that you want to aggregate these beacons up. So if you do have beacons, be more strategic about when you send them up. Like, don't send them every 30 seconds, record it every 30 seconds, but maybe deliver a payload every couple minutes, or have an accelerated tail. If you know the user's been around, the longer the user's been around, maybe the longer you can wait between payloads, because you can guarantee you've got a 5-minute interval that you'll hit. So maybe increase the length of time before you actually send the beacon up. It's really going to depend on your app, right? Like how your APIs are driven and how you make those calls. At the end of the day, I think we're probably all in agreement. You want to send the least number of requests, but you want to balance that with where the state of the antenna is and what's else is happening. Because remember, each one of these connections that you're spinning up isn't just a single SIG ACK, but if it's TLS, you've got another 5-6 packets to do a SIG ACK, just to do the handshake, and then send your payload of requesting, here's the URL resource that I want, moving from there. That also kind of begs, so I mentioned earlier about preloader, asynchronous loaders. Those are great. The challenge with asynchronous loaders is, of course, they're asynchronous, and so if you're waiting for the user to scroll to trigger the requests, how long is the user taking before they actually flip through to the next page? So I would argue that you want to evaluate your lazy load sensitivity, that perhaps you want to be a little more aggressive and having maybe a page and a half of images loaded, interactive, but not causing you don't want to trip over one of these barriers where the connection pool is being closed down without you being aware of it. Now, fortunately, HTTP2 is right around the corner for most of these devices. Within the browser arena, we've got SpeedE and HTTP2 already implemented, but they're not yet available at the OS level. So while we're waiting for Android 6 and iOS 9, which will hopefully bring, sorry, you can't read that at the bottom, which will be bringing, hopefully, HTTP2 to the OS APIs. There are a bunch of other implementations that are available in the community. So you can, these are published on GitHub. They're available for you to start tracking and implementing some of these other, especially in Android, there's already, I think OKHTTP has got a really good, well-known implementation for HTTP2. So the goal with that is that while you might be competing at the OS for a number of TCP connections, if you're using an HTTP2 connection, you're only using one. You don't have to worry about all the parallel threads or parallel connections being opened. You'll be able to reuse that one. So that's connection pools. Oh, that didn't wrap. So this is about stale caches. So that's supposed to be a milk jug. Can you see that? All right, didn't come through. I'm sure I don't know if you guys have experienced this, where apps don't play nice when they're without a network connection. Now, let's be fair, browsers don't play nice when there's no network connection either. But browsers have a number of capabilities, right? From either explicitly with service workers in Chrome, or even just having stale caches, right? Caches that are marked as available, and even if you load the page when there's no network, you'll get something. With browsers, with native apps, caching is not a guarantee. You don't, unless you've explicitly requested the object to be, the network connection to be cached, you're not going to get any caching. And this is, my real life experience of, in various states, but trying to, on an airplane, trying to fill out a customs declaration and trying to, what's my hotel address? And well, the app doesn't work because I don't have a network connection, and I don't know what my address is for the hotel. So let's. Browsers have done this for a long time, in particular it's caching. So, I don't need to belabor this point. Two big recommendations here. One, use the NSURL session. So NSURL session came in iOS 7, and it brought in a lot of the defaults that the NSURL connection didn't have. So in iOS, you had to explicitly add caching and cookie jar support and things like that. NSURL session does that for free automatically. It says you've got a cache now available within your app. There's also a private URL session that you can use if you want to keep it contained.
Do you know what the NS in front of that stands for?
Next step.
Next door?
Next step.
Oh, next step. Oh yeah, that's
The
from the
original
next. Yeah.
iOS, not iOS, God forbid, the original Unix implementation.
Yeah, it's from the old Next days, the OS X ancestry, Steve Jobs days. Yeah. And in the Android world, there is the HTTP response cache, which is a wrapper, or can be used in conjunction with the HTTP URL connection. So in the Android ecosystem. Now, just a kind of a side point here, HTTP resource cache is not compatible with the Apache HTTP client. So if you're using the HTTP client, you need to bake your own caching. But at least with Android does have the other wrapper for the HTTP URL connection. So caching. It's funny that we have to declare these things, but so many apps are built just make the network connection and not depend on any local caching, which is something you take for granted in a browser world. And again, this didn't work. All right, so let's save IPv4. So IP space is precious in SNI. If the world is moving to HTTP2, which most implementations are going to be dependent on TLS. In this TLS world, IPv4's IP addresses are required. right? For each certificate that's deployed, you need to have an IP address associated with it, just because of where it's negotiated in the stack. Now the solution, a long, very old solution now, is SNI, to offer the ability to have the client negotiate at the time of connection which certificate. So pre-SNI, the client says, I want your certificate, you get the certificate, and then the client says, that's the one I was looking for, or no, it's not the one I was looking for. And then only if you pass that first gate do you get to make the request for whatever hosting you're looking for. SNI allows you to collect this up into one IP serving many certificates and let the client negotiate that. Now for CDNs and like Akamai, this is something that we've been waiting for at SNI support, broad range, because that will allow us to make better use of the IP space out there, rather than having to depend or stick one IP or dozens of IPs per certificate. We can now collate this up into a single IP space. And as far as I know, they're not making any more IPv4s. So where are we at with IP, with SNI? So unfortunately, 15% of all TLS traffic doesn't support SNI. Now the usual case, the usual statement is, well, this is because of Windows XP. Windows XP didn't support SNI, and when Windows XP dies, we'll be able to high five and be able to support SNI shortly after. Clearly, this is not the case. Android occupies 50% of the problem because it doesn't support SNI, which is interesting by itself. And I'll explain that in a second. Windows is this 25%. A big chunk of that is Windows XP and Vista. And then you've got some old versions of iOS and Symbian and RIM. And this others category, this 15% up here, all kinds of interesting things live in that other category, from Xbox consoles. It's a myriad of devices. This is TLS supporting devices that don't support SNI. Because the problem being, if you don't support SNI, it's an all or none cut. Everybody has to support SNI, or some people are going to get left in the dust. So at this point, 15% are going to be left without SNI, without any TLS capabilities if the world flipped to SNI. So I want to break up the Android piece, because Android's problem, a good 94% of the problem, is Android pre-4.3. So some of the problem is, the 2.0, 2.2 system. So in 2.3, SNI was brought into the core OS, with the exception of the HTTP client library. The HTTP client library, the Apache client library, didn't bring SNI support in until 4.4. And so anything 4.3 and earlier that we're using, and many apps use that Apache library, they're in that big glump of applications. Post 2.3 to 4.3, anybody in there that's using HTTP client, that's 94% of these Android use cases, is because it's just the libraries that don't support SNI. And of course, all the modern browsers all support SNI, either explicitly with their own libraries, or they're depending on the OS to provide it. So the simple solution is for you to, if you're building your Android app, to help us move the world to an SNI friendly space and avoid the HTTP client. OK HTTP is a good alternative. It's pretty stable out there and uses HTTP URL connection libraries instead. So that's SNI. So the last thing I want to kind of touch on is about measuring performance. Now, in the browser world, we've come a long way. We've built nav timing to capture what's actually happening on the wire. We've got resource timing. We've got a bunch of specs that the browser provides that can be tapped into, and anybody can collect that data and beacon it back, and typically we call those RUM solutions, real user monitoring. And it's a nice, consistent way of comparing apples to apples. How does your page perform? How's after it's rendered and fully loaded? How do you track from action to action? In the app space, the native app space, no such standard exists today. It's an unfortunate situation. Now, most APMs out there, application performance monitoring solutions, do have a stab at it. They've all come out with, most of them have all come out with SDKs that allow you to embed inside your app to try to track performance. But each one of them is really dependent on you putting a start and end beacon. Start a beacon at the beginning of the load and fire another beacon at the end of the load. The OS doesn't provide you any metrics of like how much CPU or time did it take to load the app, how much time did it take to load the app, the API call, and then paint the response from that. You have to bake that all yourself. Now, there's actually a lot more interesting things that we can do that we might want to collect, not just timings. This is just a quick hit of lists of things that maybe it's more than just about the time it took to render the page, but also what is the user doing inside the page? How much time are they spending navigating around? How much time is spent in waiting for the antenna to spin up and spin down? How is battery utilization when using your app? There's a lot of other interesting things that you can finally get access to because it's a native app that you don't get as a browser. That could also be part of this tracking of statistics. But the bottom line is it's pretty nascent right now. We're early on in the story of tracking performance and capabilities. In fact, just last night, Laura Hogan was tweeting out asking, we got to do something about this. We've got, so she's actually started a gist and looking for comments and feedback about what should we be tracking? Can we start to think collectively about how to track these metrics and have a consistent story around it? My encouragement is to join the conversation. This is from yesterday, it was 3:08 yesterday. And that's kind of where we're at today. So I've just kind of hit five ways in which native apps are definitely behind where mobile apps, where the mobile browser is. And I liken the debate about native versus web is the same as cake versus pie. Pie is clearly better. And, and I might be biased as well with the web, but there's a lot that native apps can learn, and I don't think these are insurmountable items. Join the conversation, let's learn together, and I think we can definitely make a dent and make apps faster. Cool. Thank you very much for your time. Questions, thoughts? Wow. Yeah.
What's the tools that you use for measuring the app performance?
So I use it a number of different ways. So one, I took a couple passes with these different apps that I was measuring. So I was using a passive means, right? So I would either use, so they're all using a stopwatch and a camera, and I was using PCAP, so I spun up a virtual network interface just to capture packets across the cellular connection to see what was going on. The other way I was doing it was setting up a proxy and connecting, so just kind of watching the traffic through my local proxy and then seeing how performance impacted.
That is going over Wi-Fi, right? Not cell tower.
For which one?
For either case.
The PCAP is over cell. So with iOS, you can, with a tethered device, you can mirror the network interface. So locally, I created my own network interface that cloned my cellular connection. So I can, now it's from the TCP layer, so it's not the cellular connection, so it's from the TCP
but it's still like going over the cell network.
But it's over the cell network. That's why I use PCAP. And then with the the proxy infrastructure, I used a link conditioner to change the performance. And actually, one of the things I was curious about is like, does changing performance in the network actually impact the app? And the bottom line is yes, as you'd expect, right? If you're making a request to, what my recently, the sale items, or give me the description for this news item, all that's got to come across the wire. And if it's slow, your app is going to be slow. There's no short end about it, right? So yeah, link conditioner is part of OS X, Xcode.
Yeah, and Xcode's profiler is vicious in how much truth it tells you about how you're doing.
Yeah. Cool. Yeah. Oh.
Please.
Oh, have you seen or have you seen anyone use a network analyzer or something like that to figure out how like the types of requests your apps makes, how it like triggers the antenna to work?
Yes, I have seen some stuff. 7 networks, and I wanted to actually show you the stuff, but it's I didn't get the final OK to show you. But I've seen some stats that they've done where they've been looking at the signaling cost. In fact, actually, let me show you. I think I've got one slide that I can show you.
Now do
Yes.
say yes.
Okay.
Yeah. All right.
There was a hidden slide I had in here I want to show you. Boom. Right here. So they've done, research around the cost around different apps in a 24-hour period, just watching what they're doing, especially apps that poll and just periodically say, hey, do you have anything for me? Do you have anything for me? And the cost for requesting signaling time, which is this is a whole other dimension, because the cost for signaling time, the request for signaling time, eats into your total bandwidth, like your total data packet bucket, right? So even though you're not sending data, you're requesting the signaling channel to ask for time to send. That all adds up, especially if you're sending 30 signaling requests for every one attempt for an actual SIG ACK. That's a lot of extra wasted bandwidth, especially if you've got all these devices, all the devices all doing the same kind of thing. There's a lot of extra traffic sitting on the air, all requesting for their time slice and collectively slowing down the network, right? So this is more of a, the catastrophe of the commons problem, where we're all sharing these resources. That's the word I'm looking for.
Yeah.
So it's the work that they've done in sending signals. They've done some modeling of like what would happen if you were to collapse and aggregate up beacon times and even just application payload request cycles and try to condense that. And they've seen 30% improvement in battery life alone, just by shifting request times around. And so it's 30% battery, and I think a similar 30% in even performance, just because the antenna is awake and active and making those requests faster.
That makes sense.
Yeah.
I think antenna would be one of the harder things to optimize away in terms of battery life, because you always have to broadcast at a particular strength to reach your target. So
Yeah.
it's not like the screen, you can only get so efficient.
Yeah. Sorry, there's a question here, and then.
Oh, I was just thinking, I was looking it up, Twitter owns, what they acquired, Crashlytics in Boston.
Crashlytics, yeah.
And they have some pretty interesting tools for monitoring your app. I was looking to see if they were monitoring low-level performance artifacts or something, but I'll have to look later. I see that they're monitoring, how many users there were, what kind of devices, certainly all that data. I mean, Crashlytics itself, if the app crashes, it does beacon back really important data, but I wanted to know how much low-level detail they were, something like this, would they tell us, these kind of
I haven't seen, and there's a lot of different companies out there, so I kind of
you said
claim to
there's a
be the expert, but everybody's still struggling with this and trying to figure out what's the best way to collect this without pestering the user for 30 different permissions to get access to this data, just to beacon back. So it's you get security models and user experience. Yeah.
Is there a reason why they don't publish subscribe instead of doing that?
Like you mean
like instead of pull, rely on push, so Facebook mothership.
So, but push is still, it's fake. Like they're like all pushes all depend on a pull request. So there's still a request coming back to the mothership to say
You can keep the connection open. That's the trick.
Yeah. So that keep the connection open, or just interval. And so like with with iOS devices, it's going to one central location and say, do you have any messages for any other sets of apps? So you can aggregate up the requests.
No, I'm not talking about the push messages. I'm
Yeah.
talking about Facebook when the app is running.
Yeah.
Instead of them, is this for polling?
Yeah, this is polling.
So they couldn't develop something a little bit more efficient than 125 requests over 5 minutes?
This is it's every 5 minutes. This is not my research. This is Seven Networks work.
Like you don't
It's
know
interesting.
about the limitation in iOS that would prevent you from keeping an open connection or a listener for that.
Other than you do have timeouts that happen, like every
Yeah.
14 seconds. Roughly 14 seconds, the connections will start to wind down, because the OS is going to try doing the best thing for it, right? It wants to keep the antenna hot is more expensive than keeping it quiet. So rather preserve battery life. So it's going to try closing things down. So if you're constantly going up and down, as you can imagine, reading an article, then hitting the like button. Like how long is the user time?
And I bet you some of that is also keeping, even if they're waiting for something to come down, they may be beaconing to just keep it up.
Yeah. So this is not to pick on any one provider out there, but this is I think a collective challenge, because we all of our apps expect that it behaves like a browser does, right? That it we do things in batches in a browser, and we aren't doing things trickle as you do in an app. There's another question somewhere right there.
So this polling thing, I work on the e-commerce app for Wayfair, and the polling versus push question is one we're working on now. So right now, if we're in the background, we refresh the cart every 10 minutes, but what we're looking at doing is letting the system manage connections and only refresh the cart if we get a push from the server.
Mm-hmm.
And of course, that requires a little more sophistication and work on our part,
Yeah.
but we think it's going to be worth it for the users.
Yeah, especially because that pub-sub model is available in most of the OSs. Depend on the OS to drive that information to you.
And we trust that the iOS interaction with Apple's push servers is going to be managed in a more efficient fashion than we can by explicitly every 10 minutes making a request to Wayfair servers.
Yeah.
And I think that's probably what
Yeah.
the selling point is.
Yeah, absolutely. Yeah. And they're doing it anyway, right? So this is a sunk cost of a connection. It's already going out. So you're piggybacking. Cool. These slides I skipped over. If you're all interested, this is cellular connection, which they puzzle me, and I throw these in as more just words of caution. So this is me examining the PCAP, and you see my client receive window size. So when I'm advertising that I've actually got 4K receive window, or 834 bytes wide. So my device is saying, not that I can't receive that much, just that my device is saying maybe slow down in sending the data. This puzzles me mostly because I suspect it's more about the device saying I'm busy doing other things. I don't have enough time to flush my own buffers to stop sending me data, because I'm going to throw it on the floor and you got to send it again. Which I think is also a secondary editorial about where is the browser spending its time. Is it on network, or is it on GPU or CPU activity? And there's a balance, especially the long tail of devices out there. The other thing, of course, to remember is on cellular connections, you've got a lot of any kind of noisy connection, somebody turning on the microwave. I mean, this happens on Wi-Fi too, but cellular connections especially, you can have a lot of dropped packets, a lot of retry packets and things like that. It's pretty messy for cellular activity. Yeah.
Could the noise be causing the small packet sizes?
Well, that's I don't know which is which. Is it the noise that's causing it? And these are two different time periods here, but is it the client's too busy and can't flush its own buffer, and so it's dropping these packets, forcing it to be resent, waiting for the, or because they didn't send an ACK on it, or is it, some other interference?
Yeah, I was just wondering if it, let's say the client is thinking, I'm losing too many of these packets, so maybe if I shrink the size, more of them will get through versus interference.
Possibly, yeah.
Yeah, that's like a lower OSI level than app creators regularly.
Yeah.
Oh, yeah.
Yeah, exactly.
You're not supposed to know.
Yeah. Yeah. At the end of the day, it really is a cautionary tale of send small payloads, send them together, and because it's a wild west out there on the connection. So the more that you can depend on reliability, the better. Cool. Thanks for your time, guys.